Hello, my name is Delaney Taubenberger, and I will be speaking on linear regression models. There were three types of linear models tried in this project: multivariable linear regression with all predictors, and with a subset of predictors that are not highly correlated, and a robust linear model. The first multivariable linear regression model uses all the predictors against the pollution class. The results of the model are following. The root mean square error is 82.21, and the R-squared statistic is 0.22. The lower right image shows the predicted values of the pollution versus the observed values. The scatterplot's results show a solid triangle. The upper right chart shows the same shape, but with the residuals versus the predicted values. Other points of notice are that the scales of the axes are not the same. Both the predicted scales have ranges between -100 and 200, while the observed scale is between 0 and 1000. The scale of the residual is between -200 and 800. On this predicted versus observed chart, the scale should be the same and not be negative values. With all of these factors, this model is not a good fit for the data. The next model only has predictors that do not have a high correlation. In this case, a high correlation is a correlation that is above 0.80. These variables include dew and temperature. This model's RMSE is 90.06 and the R-squared statistic is 0.06. This model also has the same issues with the predicted versus the observed graph on the bottom right, and the linear regression model has with the scales. The same can be said for the predicted versus the residuals chart on the top right. This model is more limited in its predictions since the majority of the predicted values lie behind 120, with a few points going beyond this boundary. This model is once again not a good fit for the data. The last linear regression model type that was tested is a robust linear model. In this model, the data was pre-processed using principal component analysis, or PCA, and the constraint intercept was set to true like the rest of linear models. The results of the model are that the PSI sample is the best fit out of the other PSI options. The root mean square error is 89.80 and the R-squared statistic is 0.07. Like previous linear models, this is not a good model for the data. The predicted values do not reflect the scale of the observed values. The R-squared statistic is too small and does not reflect the data enough to be an effective model. Looking at the results of all three linear regression models, they're not a good way to model this data. In all three cases, the RMSE is very large. The largest root mean square error is 90.06 and the smallest is 82.21. Also, the R statistic, which shows how well the model explains the natural variation of the data, is very small. The largest R squared is 0.22 with the variables being used in the model. The smallest R squared statistic is 0.059 with the linear regression with no high correlations. Another reason is that the residuals versus the predictive plot do not show the value spread across a horizontal line at 0. In all three cases, there is a solid downward line with all the points above this line. In the scatter plots that show the predicted versus the observed values, there is no line that all of the points go around, which is what we should be seeing in a normal linear regression. Instead, we see a triangle of points that do not match at all with the observed values. Now James will discuss the regression tree model.